Welcome to Maths with EJD. I've been making a series of videos on matrices, and I think this is about the 12th one or so. But in the last three videos, I began to talk about solving systems of linear equations. In the first video under this, I talked about the use of the Cramer's rule. The second one was about the use of the matrix inversion method. So this is another method today. Well, maybe two methods lumped into one because one leads to the other. So that's why I'm putting them together. So we are talking about the Gaussian elimination stroke the Gauss-Jordan methods. Of course, we've seen how we use the Gauss-Jordan method to find to find inverses, right? The same idea is applying here. So we are basically finding inverses, except that we are augmenting the matrix of coefficients with the right-hand side, and we're eliminating until we get our answers. Then, of course, while moving towards Gauss-Jordan, yeah, you would pass through Gaussian. That's why I'm putting it together, so I don't have to create two separate videos. So as you can see, of course, the first thing you have to do if you are given a system of linear equations is to augment coefficient matrix with solution vector. We've done that something like that in looking for inverse for a matrix. So that same augmentation, except that now we are augmenting the matrix with the solution vector, that which I call the right-hand side. That's what I've been calling the right-hand side in the last video. Then for Gaussian elimination, you transform you transform augmented matrix into row echelon form. You transform the matrix into row echelon form. For Gaussian elimination, you transform augmented matrix into row echelon form. So when you augment the matrix of coefficients with the solution vector, then you transform into row echelon form. In row echelon form, all we want is we just want something like maybe A, B, C, 0, D, E, 0, 0, F. We just want everything below the principal diagonal to be 0. So as far as you can make everything below principal diagonal 0, that is row echelon form. But if you are going to the Gauss-Jordan method, you're actually transforming the augmented matrix into reduced row echelon form. In the case of reduced row echelon form, as opposed to, sorry, let me do this, augmented, okay? Then let me carefully get rid of this and, okay. So I want to just establish the difference as a summary. I've done a whole video on that, but let me just quickly show the differences between the two of them. Okay, yeah, all right. So the reduced row echelon form, you need to make the matrix like this: ABC 0 DE 0 0 F. So you need all the elements below the principal diagonal to be 0. That is the row echelon form. But then in the reduced row echelon form, which Gauss-Jordan represents, yes, you are going to have A 0 0 0 B 0 and 0 0 C, meaning that and of course in fact, beyond even just having ABC, should even be one. You're basically going to transform the matrix into a unit vector, a unit matrix: 1 0 0 0 1 0 0 0 1. So remember, the principle for row echelon form is to have just make sure each leading entry is a step to the right of the leading entry in the column above it. So this is the leading entry in the first row. For the second row, it has to shift a step, a column to the right, and this one shifts a column to the right. And then those leading entries should be the first non-zero element. So meaning that, of course, this is A already, no problem. So for this to be the leading element, it means whatever is before it has to be 0. And for L, so whatever is before it has to be 0. So technically, reducing the matrix into a form where every element below the principal diagonal is 0. But in the case of reduced row echelon form, you are literally turning the matrix into a unit matrix. And the advantage is that, of course, this will take the RREF takes more steps, but you can easily read off your solutions without even doing anything extra. But for Gaussian elimination, which leads you to row echelon form, after getting there, you have to still do a little bit of solving to get the solution. The only thing is that each of them reduces the matrix and makes it easier to solve questions. But row echelon form is easier. So once you augment the matrix of coefficients with the solution vector, then you reduce to either row echelon form or reduced row echelon form. The next thing will be to obtain the required solutions. Okay, so let's go ahead and talk about the first example. Now, one advantage of Gaussian elimination and the reduced and the Gauss-Jordan method is that you can actually use it for, I've always, in the previous two videos, right? I always gave you a 2x2 matrix first and then 3x3. But here I'm starting with 3x3 because after this, I'll be using a 4x4. Now, if you try 4x4 with Cramer's rule, of course you can do it, but that has a lot of trouble. You're going to be looking for maybe 5 matrices, and to find only one, you're going to be looking for 5 determinants, sorry. And to find one determinant alone is a lot of work, So, but the advantage of Gaussian elimination and Gauss-Jordan is that you can even use it for a 10x10 matrix without stress because you're not looking for determinants. You're just doing elementary row operation, basically. So here I'm starting with a 3x3 matrix. We want to solve x plus 2y minus z equals 5. I think it's the same problem we've been solving from the first video on solving system of linear equations. So 2x minus y plus 3z equals 12, and 3x plus 4f plus 2z equals 20. Of course, using the Gaussian elimination and Gauss-Jordan methods. And like I've told you, Gaussian elimination is a step on the way to Gauss-Jordan method. So that's why I'm putting the two together. Okay, of course, easy peasy. You already know how to make matrices out of your system of linear equations. That is not a problem, I want to believe. So, of course, 1, 2 minus 1, you have that. 3 minus 1, 3. 2 minus 1, 3, you have that. Then 3, 4, 2, you have all that. Okay, and then x, y, z, the vector of the variables, and 5, 12, 20, the vector of the solution vector, so to speak, or the right-hand side, like I've been calling it in previous videos. So now that you've made the system into a matrix form, so the next thing you want to do is to augment the matrix. Augmenting the matrix, we have, 1, 2 minus 1, 1, 2 minus 1. Then this 5 comes here. That's the augmentation we are talking about. 2 minus 1, 3, 12. 2 minus 1, 3, 12. 3, 4, 2, 20. 3, 4, 2, 20. So you rest this guy for now. Of course, it's not like it end has come. You're still going to need it in future when you get to where you're going. But then we are resting it now so we can move on. Okay, so these are augmented matrix. So the next thing we are going to do is we want to embark on Gaussian elimination. Like I told you, Gaussian elimination is a step on the way to Gauss-Jordan. Okay. Don't forget again, Gaussian elimination means you're reducing the augmented matrix into row echelon form, but Gauss-Jordan method means you're reducing the augmented matrix into reduced row echelon form, which is literally turning this one into a unit matrix so that anything you get here at the end of the day is the solution to the corresponding values of to the variables x, y, and z, And, in the case of Gauss-Jordan, you can just read off the solutions without even doing any extra step once you get to that level, Okay, so that's the augmented matrix. So let's start elementary row operation. We already know for Gauss-Jordan, all we need is to make sure all the, okay, let me use another color for this. All you just need to do for Gauss-Jordan is to ensure that everything here is 0, meaning that everything below the main or principal diagonal is 0. So once all these are 0, you have achieved Gaussian elimination. But for Gauss, okay, let me just stop there for now. When we get on, we'll talk about it. Okay, so my own method is it's easier for me to just turn everything I need to everything. I just turn everything to 1 so it can be easy for me to subtract. So, and I told you it is better to focus on things column by column. So let's focus on column 1 first. So this is already 1. So nice. That's why I'm saying the new R1 is the old R1. So, okay. So we have this like this. But then this has to be 1 because I need to subtract. I need to make this one 0. This has to be 0. So, and the way to get this one to be 1 is to multiply the whole row by half. So I have half times 2, that's 1. Half times minus 1, that's minus 1 over 2. Half times 3, that's 3 over 2. Half times 12 is 6. So I also need this to be 1, right? So then I need 1/3. 1 over 3 R3 becomes the old one becomes the new R3. So 1 over 3 times 3, that's 1. 1 over 3 times 4, that's 4 over 3. 1 over 3 times 2, that's 2 over 3. 1 over 3 times 20, that's 20 over 3. So with that done, now it's easier for us to just subtract and get zeros where we need them, not forgetting that we need this and this to be 0. But now that they are both 1, it's easy to get them to be 0. Okay. So now I need this to be this and this to be 0. So all we just need to do is row 1 is row 1 because this is already 1. Purpose accomplished. So row 1 is still row 1. And then row 2 now, this row 2, since this has to be 0, so we have to say the new row 2 has to be the old row 2 minus the old row 1. So that's 1 minus 1, 0. Minus half, minus 2. No, that's minus half, minus half, that's minus 1 over 2, minus 2 over 1. The LCM is 2. So that's 2 into 1, that's minus 1 minus 1 into, that's minus 2. So the 1 into 2 is 2, 2 times 2 is 4 rather. So that's minus 5 over 2. And that's why you have this minus 5 over 2. Then the next one is 3 over 2 minus 1. So that should be, 3 over 2 minus 1. That's 3 over 2 plus 1 over 1. LCM is 2 again. 2 into 1 times 3, 3 plus 1 into 2, 2 times 1, 2. That's 5 over 2. And that is why this is 5 over 2. Then 6 minus 5, easy peasy, 1. That is 1. So so we have taken care, we have a new row 2. Then we do the same for row 3. We subtract, we just say row 3 minus row 1, row 3 minus row 1. So row 3 minus row 1, correspondingly, we have 1 minus 1, 0. Okay, need a better marker for this. So 1 minus 1 is 0. Now 4 over 3 minus 2. Now it can get confusing. You may now be saying 4 over 3 minus half, minus half. You can get confused. Don't forget, our pivot here is 1. So we are focusing on row 1. So I've made such a mistake before. That's why I'm even saying that. So the next is 4 over 3 minus 2. So you have 4 over 3 minus 2 over 1. LCM is 3. So that's 4 minus 6. And that is minus 2 over 3. So that's why you have minus 2 over 3 here. Then 2 over 3 minus 1. 2 over 3 minus 1. That's 2 over 3 plus 1. LCM is 3. 3 in 3, 1 times 2, 2 plus 1 in 3, 3 times 2, 3. That is 5 over 3. And that's why you have this 5 over 3. Okay, so the next one is 20 over 3 minus 5. 20 over 3, 20 over 3 minus 5 over 1. 5 over 1. LCM is 3. That's 20. 1 in 3 is 3 times 5, 15. So 1 in 3, 3. 3 times 5, 15. So you have 5 over 3. And that's why this is 5 over 3. So, I mean, that's if you're under pressure, you need to be careful because you can easily make a mistake. And once you get one wrong, everything will be wrong. But if you are calm, you can be fine. Okay, so we have the matrix in red, and then we are still going on. So now we have achieved, we have 0. We have 0 here. Actually, we have achieved this. This is the achievement, actually. So we have got that. But then, since you have done with that row, the next thing is to go to the second row. And the second row, for the second row, the pivot cannot be on the first row again. It has to be here because the pivot has to be one step right to the one at the top. So this has to be the new pivot now. So again, we are going to focus on making the whole of this row 1. And what do we do? Since we have 2 here, I need to make it 1. So that's why I have the new row 1 will be half of the old row 1. Now the new row 2 will be minus 2 over 5 of the old row 2, because I need to make this one 1, which is actually the pivot now. It's the key guy. So you have to multiply minus 5 over 2 by its multiplicative inverse. The multiplicative inverse, like I keep saying, is the number by which you multiply to make it 1, which is, and in this case, that would be minus 2 over 5. Okay. And then for the row 3, this also has to be 1. So the multiplicative inverse of minus 2 over 3 is minus 3 over 2. So minus 3 over 2 of the old row, we give you the new row 3. Old row 3, we give you new row 3, minus 3 over 2 of that. Okay, so let's do that. So half of R1, so 1 times half, that's half. Half times 2, half times 2, that's 1. Half times minus 1, that's minus 1 over 2. Half times 5 is 5 over 2. So that is settled. And since that is settled, we go on to minus 2 over 5. Minus 2 over 5 times 0, 0. Minus 2 over 5 times minus 5 over 2, 1. Minus 2 over 5 times 5 over 2, that's minus 1, Then minus 2 over 5 times 1, that's minus 2 over 5. So that goes. And then we have the last row. Minus 3 over 2 times row 3 will give us the new row 3, right? So 0 times minus 3 over 2, 0. Minus 3 over 2 times minus 2 over 3, that's 1. That's the purpose why we did that. Minus 3 over 2 times 5 over 3. Minus 3 over 2 times 5 over 3. This goes out, and we have minus 5 over 2, You have this 5 over 2 there. Then minus 3 over 2 times 5 over 3, that's minus 5 over 2. Just like the one we just did. So again, we are on course now, because this is the pivot, right? So it means this has to go to well, this because for Gaussian elimination, this doesn't have to go to 0. Only this has to go to 0. But because I'll still need to get this to 0, so I just want to do the 2 at once, so I don't have to waste one more step. This doesn't have to go to 0 at all. So all we need here is for this to go to 0, basically. But I mean, because we still need that, that's why I'm doing both. So you don't have to get this to 0, but I'm doing that now. So let's do it. All right. So to get this to be 0 and this to be 0, what do we do? Since this is already 1, so the focus is on 2 now. 2 is the pivot. So you now say to get 0 here, right? So you have the old row 1 minus the old row 2 gives us the new row 1. Then row 2 is row 2 because it's 0, 1 something already, so no problem. Then the old row 3 minus the old row 2 is the new row 3. So for this now, let's do it. R1 minus R2. So you have R1 now, R1 minus R2. So half minus 0, you have half. 1 minus 1, you have 0. Then minus half minus minus 1, that's minus half plus 1 over 1. LCM is 2. That's minus 1 plus 2, and that is 1 over 2. So that's why you have this. Then you also have the next one, 5 over 2 minus 2 over 5. That is 5 over 2 plus 2 over 5. The LCM is 10. 2 in 10 is 5. 5 times 5 is 25. Plus 5 in 10, 2. 2 times 2, 4. So you get 29 over 10. So this is why you have this 29 over 10. Okay, so row 2 is row 2. So no worries. Row 2 is row 2. So because row 2 is row 2 now, we just bring this row 2 exactly the way it is. We fix it there. Then row 3 needs some work because this has to be 0. So, and what do? We say the old row 3 minus the old row 2. So 0 minus 0, you get 0. 1 minus 1, you get 0. Minus 5 over 2 minus minus 1, that's minus 5 over 2. Minus minus 1, that's minus 5 over 2 plus 1 over 1. LCM is 2. 2 into 1 times minus 5, that's minus 5 plus 1 into 2, and that is minus 3 over 2. That's why we have minus 3 over 2 here. And then the other one, it's row 3 minus row 2. So we have minus 5 over 2, this, minus 2 over 5, that's plus 2 over 5. These things can be tricky, so you have to be very calm when you're doing this. So 2 in 10 is 5. 5 times minus 5, that's minus 25, plus 5 and 10, 2 times 2, 4. So you have minus 21 over 10. So that's why we have minus 21 over 10 here. Okay, good news. If all you wanted was Gaussian elimination, we have arrived because all we need is to make sure that below the principal diagonal, every other thing is there, everything is 0. Okay. No, we didn't, like I told you, we didn't need it to be 0, but I just did that ahead because I know I still need that to be 0. So it's not necessary to make this 0. If all you want to do is Gaussian elimination. Okay. So, but that now that you have it, it's not a problem. So now this is Gaussian elimination done. Check. That's why I said Gaussian elimination completed. So if all you wanted to do was Gaussian elimination, the next thing you now need to do is to try to, okay, well, I went further to make things easier because working with fractions can also be a problem. So what I just did to make things easier here, of course, from here, you can already begin to go out and get this result. But to make things easier, I just wanted to make every fraction, especially in this part, you want to make every fraction 1. And to do that, I just multiply. So the old row 1, I multiply by 2 to get all the fractions out, multiply by 2. Then, of course, this minus 1, I want to get it to be positive. It doesn't have to be, because from here alone, we can read it, we can just expand things and get the solutions. But this removing the fractions make things easier. Okay, so the old minus of the old row 2 is giving us the new row 2, Then minus 2 over 3 because of this guy. Minus 3 over 2 over the old row 3 gives us the new row 3. So let's do that one after the other. So we have minus 2 times R1. So 2 times R1. 2 times half is 1. 2 times 0 is 0. 2 times half is 1. 2 times 29 over 10, of course, that's 29 over 10 times 2 over 1. 2 cancels 2. 2 goes, that's 29 over 10 times 2 over 1. 2 here is 1. 2 here is 5. So that's why you have 29 over 5. Okay. Next, you have, so negative of old row 2 is now row 1. Is now the new row 2, sorry. So minus of 0 is 0. Minus 1, that's minus 1. Minus 1, that's plus 1. The minus 2 over 5, you have 2 over 5. So that takes care of row 2. So the new row 3 would be minus 2 over 3 of the old row 3 because of this, which is also supposed to be a pivot. This is expected to be a pivot. So I'm actually preparing the ground for the next journey. Although this is like Gaussian elimination is like a stopover on your way to some other destination, like I've been saying. So minus 2 over 3 times 0 now is 0. Minus 2 over 3 times 0, another 0. Minus 2 over 3 times minus 3 over 2, that's 1, which is a pivot actually. And then minus 2 over 3 times minus 21 over 10, minus 2 over 3 times minus 21 over 10. 3 here is 1, 3 here is 7, 2 here is 1, 2 here is 5. Minus and minus is plus. So you have 7 over 5. So this is why you have 7 over 5 right here. So since Gaussian elimination has been achieved already, because all the elements under the principal diagonal, all the elements are now 0. All these guys are 0. That is Gaussian elimination achieved, because that is like row echelon form. So the next thing you want to do is you now want to get your answers, right? So all you just need to do is to, X, Y, and Z that they were resting. So you have to bring them back now. So you have this one that you have, you put it here, and then you bring back your X, Y, Z, and then you have your 29 over 5, 2 over 5, 7 over 5. You have that here. So you're going to do what is called backward substitution. So what is happening here is backward substitution. Substitution. I'm not one of the mathematicians that will tell you, because I'm a mathematician, I don't care about English, Substitution. If you get A1 in maths, you should get A1 in English, Backward substitution. Okay, so now from what we can see already, if you work this out, if you work this out, you see that this is, if you do the normal XYZ 3 times thing that I talk about all the time, because this is a 3 by 3 matrix and 3 by 1. So XYZ So if you put 101 over it, you are going to get x, y times 0 is 0, x and z equals 29 over 5. That's why we have this. And then the next one, you have y. So if you have, for this next one now, you have, okay, let me just do it by the side, x, y, z again, and you have, sorry, that is, yeah, okay, sorry, x, y, z, that's okay. X, y, z, 0 minus 1, 1. So that's minus y plus z. So you have minus y plus z is 2 over 5. And of course, the last one, if you do x, y, z, this is 0, 0, 1. So that means z is straight 7 over 5. So by doing this, you automatically have got your z. So you see, that's one advantage of Gaussian elimination, because here now the matrix has been reduced this way. So you can easily get z straight off. So you have z is 7 over 5. And because z is 7 over 5, so this one is minus y plus z, this is x plus z. So it's okay. You can just put 7 over 5 there and you get x and y respectively. And that's what we are doing. So you have so from here now, we have that. We have minus y plus z is 2 over 5. Minus y plus z is 2 over 5. And we know z is 7 over 5 already. So here, I'm making this happen. So because, I don't like minus as much as possible. So I just transfer y to the other side. And then I bring 2 over 5. So that's 7 over 5 minus 2 over 5. Then y goes. And that's equal to y, right? 7 over 5 minus 5 over 5 is actually, of course, the LCM is the same. 7 minus 2 is 5 over 5. And y is 1. So we have got we have got z to be 7 over 5. You see, it's called backward substitution because you get z, you get y, and then you now go back to get x. So, and this is you getting x here. So also x plus z is 29 over 5. So you have x plus z, which is 7 over 5, equals 29 over 5. Now, in this case, there's no minus problem like before. So I just say x equals 7 minus, 29 over 5 minus 7 over 5. The LCM is the same, so I just say 29 minus 7, that's 22 over 5. So for Gaussian elimination, you have arrived, and this is your answer. X is 22 over 5, y is 1, and z is 7 over 5. So if you are doing Gaussian elimination, that is how you go. But so if your stopover is here, then that's all. But then we are still going to go to Gauss-Jordan. We are going to Gauss-Jordan. Where did we stop? So for Gauss-Jordan now, we take the step in Gaussian elimination and we continue our journey. So those who will stop over, they will process themselves and get their answers. But for those of us still going to Gauss-Jordan, we come. So all I'm doing is I'm just transferring this matrix, this Gauss-Jordan matrix now. So I just have 1, 0, 1, 0 minus 1, 1, 0, 0, 1, then 29 over 5, 2 over 5, 7 over 5, just that matrix. So that's what we're bringing. And then, so what we need again is for Gauss-Jordan, we now need this to be 1. It's minus 1 now. We need this to be 0. We need this to be 0 because this is also a pivot. So all these pivots should be 1, and all these pivots should be 1. Every other thing below or above them should be 0. So that's what Gauss-Jordan wants done. So, and because this, I was actually seeing this future, that's why I already made sure all these ones are 1. So we can easily take care of, since this is the pivot now, so we can have the new row 1 will now be, because we need this to be 0, right? So the new row 1 can be the old row 1 minus the old row 3. So that is old row 1 minus the old row 3. So that is, of course, 1 minus 0, this 1 minus 0, that's 1. 0 minus 0, that's 0. Then 1, this 1 minus this 1, that is 0 up here, And then 29 over 5 minus 7 over 5, we just saw something close to that. That's 22 over 5. And then for the second row, right? For the second row, what do we do? The second row needs to be 0 also. This also needs to be 0. What do we do now? We just say the old row 2 minus the old row 3. So 0 minus 0, we have 0 here, -1 -1 minus 0, that's -1. Then 1 minus 1, 1 minus 1, that is 0 here. Then, of course, because this is already 0, 0, 1, and that's what we want for a 3 by 3 matrix, 0, 0, 1. So we just leave row 3 the way it is, 0, 0, 1, 7 over 5, 0, 0, 1, 7 over 5. So that is maintained on our way to Gauss-Jordan, having left Gaussian elimination. Okay. By the way, maybe in one video I'll talk about, maybe I'll do some history of mathematics. There are some names you always come across when you're doing math, like Gauss, like Bernoulli, like Cauchy, and all those people, you know. So now that we have achieved this, the next thing we want to do is that, okay, this is, everything looks almost good except for this minus, because this minus has to be this, it's a pivot, so every pivot has to be 1. In reduced row echelon form, they have to be 1. So it looks like that's the only thing left to do. So the old row 1 is the new row 1, the old row 3 is the new row 3, but then the old row 2, for the new row 2 has to be the negative of the old row 2. So we have minus times 0, 0, minus times minus 1, that's 1, minus times 0, 0 again, minus 1, that's plus 1. And with this, once you can get a unit matrix, the corresponding unit matrix, right? Once you can get this, then that means that you have arrived. This is your unit matrix. The old matrix the original matrix of coefficients has become a unit matrix. So the beauty of the Gauss-Jordan method is that you can read off the answer straight. In fact, if it was OBJ, you don't have to do anything for that. You just know straight that this is your X is 22 over 5, your Y is 1, and your Z is 7 over 5. So it takes more steps, but then you don't have to do anything so much extra like you did before. So here, for the sake of formality, right, I'm just saying, okay, now that you have this, you can now remember X, Y, Z again. So you have now you have unit matrix multiplied by X, Y, Z equals 22 over 5, 1, 7 over 5. And I told you the unit matrix is more like 1 in the sense of numbers. So this is like multiplying. If you even try it, you do X, Y, Z, X, Y, Z, X, Y, Z. If you try it, you get 1, 0, 0, 1, 0, 0, 1. Oh, sorry, 1, 0, 0, right? For the first row. For the second row, 0, 1, 0, 0, 1, 0. For the third row, 0, 0, 1, So here you just have X. All this will go. Here you have only Y. This and this are gone. Here you have only Z, and this are gone. So that's why X is 22 over 5. Y is 1. Z is 7 over 5. So just like we got for Gaussian elimination, except that we had to do a bit more arithmetic. So either whatever you want, you have it, whether you want Gaussian elimination or Gauss-Jordan. Gauss-Jordan takes more steps, but at the destination, things are obvious. The results are direct. You can see them. Okay, so that's a 3 by 3 matrix. So for the first time, let's solve a 4 by 4 matrix. Of course, you can't even try this. You can't try a 4 by 4 thing with the previous method. Like, okay, well, you can try, right? You can do it, but it's more complicated, especially when you need determinants. Getting the one determinant alone is a big trouble. So that's why Gaussian elimination and Gauss-Jordan are very excellent once you are beginning to talk about 4 by 4, 5 by 5. In fact, you can even do 10 by 10. Just follow your row operations perfectly. So example 2, we have this 2x1 plus x2 plus 2x3 plus x4 equals 6. x1 minus x2 plus x3 plus 2x4 equals 6. Then we have 4x1 plus 3x2 plus 3x3 minus 3x4 equals minus 1. And then 2x1 plus 2x2 minus x3 plus x4 equals 10. Of course, we want to do this using Gaussian elimination and Gauss-Jordan. And like I told you, Gaussian elimination is a stopover on the way to Gauss-Jordan. Okay. All right. So the first thing is write this in matrix form, extract the coefficient matrices. So here you have 2, 1, 2, 1. That's why you have this. Then you have 1 minus 1, 1, 2. 1 minus 1, 1, 2. Then you have 4, 3, 3 minus 3. That's why you have this. 2, 2 minus 1, 1. 2, 2 minus 1, 1. And then you have the vector of variables, the vector of x1, x2, x3, and x4, which you're looking for, and you have the vector, this solution vector, so to speak. So, or the right-hand side, that's 6, 6 minus 110. So now that that is done, now one thing you see with matrix is that, like, once you turn things to matrix, they look more meaningful. If you have observed, they tend to look more meaningful, and that is why in programming, like software engineering or data analysis or all that, it's easier when, like, most things are handled like matrices. So when you're coding, you are thinking in terms of matrices. So you want to see how you can transform whatever problem you have into a matrix, so you can, handle them as a unit. Okay, so the next thing is to augment the matrix. So you augment this matrix with, this matrix. Now you augment it with the solution vector, like I said, and this is the augmented matrix. So the next thing to do is, on the way to Gaussian elimination, of course, all you expect, this is the principal diagonal, So for Gaussian elimination, once you can get this, and this to be 0, that is Gaussian elimination for you. But if you now want to go further to, Gauss-Jordan, that's when you now need, in addition, this one has to be 0, this 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 has to be 0, and this has to be 0. So that's the extra if you are going to Gauss-Jordan. Okay, so let's go on. Of course, there's no way you get to Gauss-Jordan without passing through Gaussian elimination. So that's why I lumped the two together. Okay, so let's start. And I told you, like, previously, that you should do column by column, deal with them column by column, so you have a process, you have a procedure. And that, as a programmer, if you are a programming person or a data scientist or something, it's better to have this kind of algorithmic thinking, So first column, let's see how to deal with that. First column, the first thing you want to do is get everything to be 1, so it can be easy to subtract. You don't have to do it that way. There are other ways, but I don't like those other ways. So to get this to be 1, of course, you just multiply row 1 by half. So that's half times 2, that's 1. Half times 2. So half times 1, that's half. Half times 2 here is 1. Then half times 1, that's half. Half times 6, 3, right? So that's that. Then for row 2, interestingly, the first element is already 1, so we don't have to worry. So we just say the new row 2 is the old row 2. So we have whatever we have here is just what we bring over here. So that is settled. Then the next thing is 4. So to get 4 to be 1, we have to multiply row 3 by 1 over 4. So we have 1 over 4 of the old row 3 is the new row 3. So 1 over 4 times 4, that's 1. 1 over 4 times 3, 3 over 4 times 3 again, 3 over 4 times minus 3 over 4 times minus 1 over 4. Then, of course, to get this to be 1, we just need to multiply by half, okay? So 1 over 2 times 2, that's 1. 1 over 2 times 2, another 1. 1 over 2 times minus 1, that's minus 1 over 2. 1 over 2 times 1, that's 1 over 2. 1 over 2 times 10, that's 5. Right? So it's simple, but tricky. So you have to be very careful. You have to be very careful. So now we have done, we have treated, we have made everything 1. So all we just need to do now is to start subtracting correspondingly. So row 1 remains row 1 because it's now 1. So row 1 is 1 and all that. So row 1 remains row 1. The old row 1 is still the new row 1. But then for row 2 now, because we need all this to be 0, so we have to subtract, we have to subtract row 1 from each one. So that's why the new row 2 is the old row 2 minus row 1. Row 2 minus row 1. So 1 minus 1, 0. Minus 1, minus 1 over 2. That's like minus 1 over 1. LCM is 2. 1 into 2, that's minus 2 minus 1. That's minus 3 over 2. That's why we have this. Then 1 minus 1, 0. 2 minus half. That's 2 is like 4 over 2. So 4 over 2 minus 1 over 2, that's 3 over 2. Then 6 minus 3, easy, 3. Okay. So we go to row 3. What is the new row 3? The new row 3 is the old row 3 minus the old row 1. So the old row 3 minus the old row 1. So 1 minus 1, 0. 3 over 4 minus 1 over 2. 3 over 4 minus 1 over 2. LCM is 4. That's 3 minus 2 in 4, 2 times 1, 2. That's 1 over 4. That's why you have this. Then 3 over 4 minus 1, 3 over 4 minus 1 over 1. That is LCM 4. 3 minus 4. That's minus 1 over 4. Minus 1 over 4. That's why we have this. Then we have, old row 3 minus old row 1. So that's minus 3 over 4 minus 1 over 2 now. So minus 3 over 4 minus 1 over 2. Again, LCM is 4. That's minus 3 minus 2 in 4. That's 2. That's minus 5 over 4. And then you have this. Okay. Again, we have still on that, minus 1 over 4 minus 3. Minus 1 over 4 minus 3 over 1. LCM is 4. So 4 in 4 is 1. That's minus 1 minus 1 in 4. 4 times 3, 12. That's why we have minus 13 over 4 here. Okay. So tricky, simple, but you have to be careful because you're dealing with so many numbers. Then row 4, the new row 4 is the old row 4 minus the old row 1. One mistake you can make here is once the columns are getting many, you can be subtracting row 2 from row 4 and you miss it all up. So you have to be careful. So if you can draw arrows like I'm drawing or something, maybe it can help. So the old row 4 minus the old row 1, correspondingly 1 minus 1 minus 1, 0. 1 minus half, of course, that is half. Minus half minus 1. 1 is like 2 over 2. So minus 1 minus 2 over 2, that's minus 3 over 2. Then half minus half, 0. Then 5 minus 3, 2. Easy. So that is taken care of. So since that is taken care of, can we then focus on the second row? So for the second column, rather, let's focus on the second column. For the second column, right, now the pivot has to be minus 3 over 2. I mean, that the pivot is on row 2, rather, not minus 3 over 2. Pivot is row 2. So, and currently we have minus 3 over 2. That the way to get rid of that is to multiply by the multiplicative inverse, which is minus 2 over 3. So, of course, we also need all the other numbers below and above it to be 1. So that's the mission now. The mission is to get all those to be 1. So in this case, now to get this to be 1, we have to multiply the old row 1 by 2. So old row 1 by 2, that's 2 times 1, 2. Of course, you need this to be 1, right? But you can trade it off for now because since everything below it is 0 and you get all this to be 0, it's easy to get back to 1, So 2 times old row 1, that's 2. 2 times half is 1. 2 times 1, 2. 2 times half again is 1. 2 times 3, 6. Then this is minus 3 over 2. That's minus 3 over 2. This minus 3 over 2, you want to get it to be 1. So you have to multiply by minus 2 over 3. So minus 2 over 3, minus 2 over 3 times the old row 2. So that's, of course, times 0, that's 0. Times minus 3 over 2, that's 1. Times 0 again, 0. Then 3 over 2 times minus 2 over 3. This cancels out. And you have minus 1. That's why this minus 1 is here. Then minus 2 over 3 times 3. 3 cancels 3. So you have minus 2 here. Okay. All right. So the next one, we need this to be 1, right? So all we just need to do is multiply through by 4. So 4 of the old row 3 gives us the new row 3. So 4 times 0, 0. 4 times 1 over 4 is 1. 4 times minus 1 over 4, that's minus 1. 4 times minus 5 over 4, that's minus 5. 4 times minus 13 over 4, that's minus 4. Minus 13, sorry. And then for the row 4, old row 4 is, we have half here and we need 1. So multiply through by 2, multiply this through by 2. So you get this. So 2 times 0 is 0. 2 times half, 1. 2 times minus 3 over 2, 2 cancels out. So you have minus 3. 2 times 0, that's 0. 2 times 2 is 4. So we have those corresponding elements like that. So we move on. So, we have just made everything 1 to facilitate our subtraction. Don't forget our pivot now is this because we're focusing on column 2. So that's our pivot now. So all we just need to do is subtract everything from it and put it in that place. So the new row 1 would be the old row 1 minus the old row 2. So that's row 1 minus 2. So that's 2 minus 0, 2. 1 minus 1, 0. 2 minus 0, 2. 1 minus minus 1, that's 1 plus 1, that's how you have 2. 6 minus minus 2, that's 6 plus 2, which is 8. That. And of course, since the element, the pivot is already 1, so no worries. So the old row 2 is the same as the new row 2. So no stress, no stories. And then, okay, don't forget the pivot is here because it can be confusing because you have many more columns now and rows. So the new row 3 now, okay, the new row 3 is going to be the old row 3 minus the old row 2. The old row 3 minus the old row 2. So 0 minus 0 is 0. 1 minus 1. That's yeah, row 3 minus row 2. 1 minus 1, 0. Minus 1 minus 0, minus 1. Minus 5 plus minus minus 1, that's plus 1. That's minus 4. That's why you have this. Then you have minus 13, minus 13, minus minus 2, that's minus 13 plus 2. You are owing 13, you have 2, you pay 2, you are still owing 11. That's why you have minus 11. Okay. So then we go for row 4. For row 4 now, because we need this to be 0, so we have the old row 4 minus the old row 2 because we are talking about column 2. So again, 0 minus 0, 0. 1 minus 1, 0. Minus 3 minus 0, minus 3. 0 minus minus 1, 1. 4 minus minus 2, 6. So that is settled. So you can see that we have 0, 1, 1, blah, blah. I mean, this look good now, except for this that is 2, which you can easily get rid of. So now we shift our focus to column 3. Our focus is now on column 3. And in column 3, the pivot is this guy. So we need to make this one 1. I want to make everything 1 first before we can subtract. But this is the pivot, don't forget. So, and what do we do? To get this to be 1, we have to divide through by 2. So that's half times 2, 1, half times 0, 0, half times 2, 1, half times 2, 1, half times 8 is 4. So that's for our new row 1. For our row 2, right? For row 2, because we already have 0 here, and we are supposed to make it 0, so it's already 0, so no worries. So the old row 2 is still the new row 2, so nothing has changed. Then we go to row 3. That's where you have the pivot because it's column 3, so the pivot has to be in row 3. So, and it's negative right now. All we just need to do is to multiply by minus 1. So minus 1 times 0, 0. Minus 1 times 0, 0. Minus 1 times minus 1, that's 1. Minus 1 times minus 4, that's 4. Minus 1 times minus 11, that's 11, you know. So that way, row 3 is also sorted. Since it is sorted, then you can now go for row 4. You need this one to be 1. And the multiplicative inverse of minus 3 is minus 1 over 3. So you multiply row 4 by minus 1 over 3. So minus 1 over 3 times 0, 0. Minus 1 over 3 times 0, 0. Minus 1 over 3 times minus 1 over 3, that's 1. Minus 1 over 3 times 1 is minus 1 over 3. Minus 1 over 3 times 6, minus 1 over 3 times 6 over 1. 3 here is 1, 3 here is 2. So that's why you have minus 2 here. So, of course, with the way things are now, we still have, we need to get this one to be 0 because, okay, okay. Yeah, I still have a step, right? We've only made everything 1. We need to subtract. So don't forget, this is the pivot. This and this have to be 0. Okay. So what do we do? So you have to say now that the old row 1 minus the old row 3, correspondingly. So, and then that will be your new row 1. So how do we do it? So once you get that, you take it back to that row. So 1 minus 0. Take note, you can easily say 1 minus 0 row that for row 2, that's wrong. It's now row 3, row 1 minus row 3. 1 minus 0, that is, and the answer will be on row 1, sorry. 1 minus 0, back to row 1, that's 1. 0 minus 0, 0 minus 0, you have this. Then 1 minus 1, you have 0. Then 1 minus 4, that's minus 3. I think I stumbled over this the first time I did it, so careful. Then 4 minus 11, that's minus 7. Carefully done. And then, row 2, we have row 2 where we want it, so we are fine. So row 2 needs to be 0, and it's already 0. So the old row 2 is still the new row 2. So no worries. Then for row 3, this is already 1. The old row 3 is also the new row 3 because we want 1 there and 1 is already there. Then the last row 4, this has to be 0, So that's why we say the new row 4 is the old row 4 minus the old row 3. So, and the answer will be at 4. So 0 minus 0, 4, 0 minus 0, 0 minus 0, 0, 0 minus 0, 0, 1 minus 1, 0, then minus 1 over 3, minus 1 over 3, minus 4 over 1. LCM is 3, that's minus 1 minus 12, and that's why this is minus 13 over 3, minus 13 over 3, because it's row 4 minus row 3, Then here, row 4 minus row 3, that's minus 2 minus 11, that's minus 2 minus 11, that's minus 13. Now, we have reached a stopover, that we call Gaussian elimination. Why? Because this is the principal diagonal, and then everything below it is 0. So from here now, if this is where you want to stop, then you can just bring back your x1, x2, x3, x4 and write it out. So I didn't bother about that here because I know I've explained it before. So if you want to do that, just bring it together. Let me not waste time with that, because you can refer to the other example to complete that. If all you want to do is Gaussian elimination, you just stop here, bring back x1, x2, x3, x4, and do backward substitution. In fact, I can already see this is x1, x2, x3, x4. I can already see that minus 13 over 3 x4 is going to be equal to minus 13. It's going to be equal to minus 13 if you point that out, if you do that. So I mean, that's multiplied through by 3 over 13, or minus 3 over 13. So you're going to get x4 equals minus 13 times minus 3 over 13. So this cancels out, and x4 is going to be 3, I think. So watch out, x4 should be 3. That's what this is telling us. But of course, you already know how to take care of that from the previous example. So that's why I'm not worrying about getting the solutions there, because we are on a journey. So, and that's all I say. Don't settle until you have arrived. If where you are is not where you want to be, keep moving. All right. Okay, so let's see. So Gaussian elimination is completed at this stage. So now we proceed. Now in proceeding now, I mean, everything looks even good already because of what the things I've been doing. So all we just need to do now is to make sure this is 1 and all these are zeros, all these are zeros. So because this is now pivot for the 4th column, so let's move. So we need to make everything here 1. We need to make everything in the 4th column 1. That's the next journey. That's my style. So, and what do we do? So to make this to be 1, we need to multiply row 1. We need to multiply the old row 1 by minus 1 over 3. So minus 1 over 3 times 1, minus 1 over 3, minus 1 over 3 times 0, 0, minus 1 over 3 times 0, also 0, minus 1 over 3 times minus 1 over minus 3, that's 1, minus 1 over 3 times minus 7, that is 7 over 3, minus and minus 7 over 3. So that's settled. Then the old row 2 now, we need to make this one. It's minus already, so we can just change it to minus. Multiply through by minus like this. So you have minus 0, that's 0, minus 1, that's minus 1, minus this, that's 0, minus minus 1, that's 1, minus minus 2, that's 2. All right. So row 3 now, we need to make that 4 into 1. And what do? We just multiply through by 1 over 4. Multiply this through by 1 over 4, and you get this. So 1 over 4 times 0 is 0. 1 over 4 times 0 is 0. 1 over 4 times 1, 1 over 4. 1 over 4 times 4, that's 1. 1 over 4 times 11, 11 over 4. So that takes care of row 3. And row 4, we need this to be 1 in row 4, right? So we just multiply by the multiplicative inverse, which is minus 3 over 13 of R4. So minus 1 over 13 of this. So, times this is 0, 0, 0, 0. And this will give you 1. And then minus 13 times minus 3 over 13, that just gives you 3. And with that, you have made it easier to subtract. So you can get something that you want. So here we want this to be 0, 0, 0, and this is the pivot. So the pivot is that thing you always subtract, that you always subtract from others to get what you want. So to get row 1, now we need this to be 0. To get row 1, I need to say row 1, the old row 1 minus the old row 4. That is what will give me the new row 1. Look at that. That's minus 1 over 3 minus 0. That's minus 1 over 3. 0 minus 0. That's 0. 0 minus 0. That's 0. Then 1 minus 1. That's 0. That's the purpose. And 7 over 3 minus 3. 7 over 3 minus 3 over 1. LCM is 3. That's 7 minus 1 in 3, 3, 9. So that's why you have minus 2 over 3. This is 7 minus 9 is minus 2 over 3. That's why you have minus 2 over 3 there. Okay, so the next thing is to get 0 here, and that's why the new row 2, this is the new row 2, is the old row 2 minus row 4. So row 2 minus row 4. So 0 minus 0, 0, minus 1 minus 0, minus 1, 0 minus 0, 0, 1 minus 1, which we really need at 0. Then 2 minus 3, 2 minus 3, that's minus 1. Okay, so we have the new row 2 sorted. Then we now, for row 3 now, we need this to be 0, you know. So what do? The new row 3, we get that by subtracting row 4 from it. So row 3 minus row 4, the old row 3 minus the old row 4, 0 minus 0, 0, 0 minus 0, 0, 1 over 4 minus 0, 1 over 4, 1 minus 1, 0. You know, this is the pivot. Then 11 over 4 minus 3, 11 over 4 minus 3 over 1. LCM is 4. So that's 4 in 4, 1. 4 times 1 times 11, 11 minus 1 in 4, 4 times 3, 12. That's minus 1 over 4. So that's why this is minus 1 over 4. Minus 1 over 4. Okay. So now row 4 is where we want it to be. So it's cool. We just repeat. The old row 4 is still the new row 4. Settled. So we have 0, 0, 1, 3, like that. So we are gradually almost there. The only thing now is that, you know, we can see we only have the leading entries, you know, which would have been fine if we were dealing with row echelon reduction. But now we need them to be 1 in reduced row echelon form. We need all of these guys, all of these elements to be 1. So all we just need to do, we already have the trick of taking care of making things come back to 1. Since 1 is multiplicative identity, all you just need to do is multiply each number by its multiplicative inverse, so you can get the multiplicative identity. So usually it's like you know, a number times its multiplicative inverse gives you the multiplicative identity. A number times its inverse will give you the identity under that operation. So that's for matrix, right? The same applies for numbers, like minus 1 over 3 times its multiplicative inverse, which is minus 3 over 1, we give you 1. So that's what we want to do. That's what we want to do here. So because of that, we say that minus 1 over 3, we multiply the whole of the old row 1 through by minus 3, like that. So minus 1 over 3 times 3, we have 1. So since you have 0 here, everything becomes very sweet. Minus 3 times 0, 0. So minus 3 times 0 is 0. Minus 3 times 0 is 0. Minus 3 times 0 is 0. And then minus 2 over 3 times minus 3 over 1. This cancels, and the answer is just 2. And that goes. And then for the second row now, this is negative. So it means you just multiply through by minus 1. So the new row 2 is going to be the old row 2 multiplied by minus 1. So you have minus 0, minus and minus 1, 1, 0, 0, 1, like that, you know. So, and for row 3 is 1 over 4. We just need this to be 1. The multiplicative inverse of 1 over 4 is 4 over 1. That's why by multiplying the old row 3 by 4, you get the new row 3. So 4 times 0 is 0. 4 times 0 is 0. 4 times 1 over 4 is 1. 4 times 0 is also 0. 4 times minus 1 over 4 is minus 1. Okay? And then row 4 is row 4. I mean, it's 001, which we want, and then we have it as we like it. So taking care of that, now you can see that this is unit matrix for a 4x4 matrix. So you can see this is your I. So obviously this will be your solutions, this will be your solution. So if you're writing a multi-choice question and you don't have to show workings, so this is a nice place to stop. You don't even have to stress yourself further. So you just know this is your 2, 1, -1, 3. This is x1, x2, x2, x3, and x4, like that. So you don't have to stress yourself if it is just in an exam and you're not required to show your work, to write stories. So you can read off the answers directly. So I mean, for the formality of it, we just do unit matrix. Unit matrix is like 1 for matrix. Unit matrix, then you have x1, x2, x3, x4. You bring it back, to show you that you have not forgotten it. Then you have 2, 1, -1, 3. And if you multiply anything by 1, you get that thing. That's why you have this. And then you have 2, 1, -1, 3. And then if you read that off, it means x1 is 2, x2 is 1, x3 is -1, and x4 is 3. Remember, that's what we got for Gaussian elimination too. So with this, you have arrived at your solution. So this may look very tedious, right? But if you try that with matrix inverse method or Cramer's rule, which requires determinant, that's going to be a lot of stress. In fact, maybe triple difficult, So, but if you can master this, so that's why Gaussian elimination is a very nice tool for when you have when you have something starting from 4x4. So because I want you to also be very good at this, you can try your hands on this exercise. It's been a tedious journey up to this point. So, I mean, you want to try your hands to make sure your hands are strong with these things. So if you have ideas for me to make this better, let me know. If you have questions for me at any point, you can put it in the comment section, which we can both attend to. We can find time to do that. Thank you for listening. See you in the next video.